Okay, thank you very much. So I want to talk about very recent work I've been doing. And so it's about exceptional collections and derived categories of coherent sheaves. And the point I want to make today is that even having numerically exceptional collections is quite restrictive on the geometry of the varieties. So maybe not everyone's familiar with exceptional collections and categories. So maybe I'll make some quick recap on the objects we consider. So if we have T, a triangulated category, and if we have A and B, two strictly full sub-triangulated categories. So strictly full means it's stable under shift and cone. So maybe I should remind what the cone is. So if you have T1 and T2, two objects in T, and a morphism between T1 and T2, then the cone of F is just something that completes a triangle. So I have T1, T2, cone of F, and so this is a distinguished triangle. Okay, so that's for the basic. And so there's a definition that came up maybe 20 years ago or something like this, which is the notion of a semi-orthogonal decomposition. So you write T is equal to AB. So this is called a semi-orthogonal decomposition. If, so there are two conditions. So the first condition is actually the semi-orthogonality condition, which is that there are no morphisms from B to A. Okay, so because the subcategories are strictly full, I mean, I don't put any dots here because you can shift and take any degrees. And the second one, sorry?
The condition is missing.
Oh yeah, sorry. So 0. There are no morphisms from the right to the left. And then the second condition just says that A and B generate T. So what does that mean? That means that for all object T and T, T fits in an exact triangle. So there exist TB and TA. So this one is in B, such that so we have a distinguished triangle. Okay, so just to make things clear, I'm going to define a semi-orthogonal decomposition with more than two objects. So in that case, we have A1, AN. So this is a semi-orthogonal decomposition if. So again, first condition, there are no morphisms from the right to the left, so AI, AJ is 0 for all I bigger than J. And the second one, which is the generation condition, is just that, so for all element T and T, there exists, so such that the cone an AI. So you can check that when you have two subcategories, it's the same definition. Okay, so this is the general setup of semi-orthogonal decompositions. So, so now the question is, given a triangulated category, when is it possible to split off strictly full subcategories? So maybe the first kind of objects to consider are the simplest ones, and I mean the simplest maybe triangulated category maybe is the bounded derived category of k vector spaces. So for k field, so I didn't specify, but the categories are k linear, and so the natural thing to do is to split off copies of this simple triangulated category. So when is this possible? Well, basically we want to start with, we want a fully faithful functor from this dB of k vector spaces into T. So, if you consider a functor, so a triangulated functor from dB of k vector spaces to T. Okay, well then, so this category is generated just by the vector space k placed in degree 0. So it's enough to specify the image of k, so k placed in degree 0. So call it E, and so basically call this phi E. Well then, phi E of so this category just consists of graded vector spaces. This is just v dot tensor E. Okay, and so I write a joint, just given by by this. And so if you compute phi E of v dot, you get E tensor v dot. So basically the upshot is that this functor is, so phi E is fully faithful if and only if and only if star E. So this is k in degree 0 and 0 otherwise. Okay, so this leads to the definition of, so this is very classical, the definition of an exceptional object. So an object E in T is exceptional if okay, so k in degree 0. Okay, so what does that mean concretely? So I'm going to come to this later on, but in the derived category, for example, a sheaf will be exceptional if its endomorphism group is k and if there are no x. Okay, and so an exceptional collection is just a collection of exceptional objects which are semi-orthogonal. So here, of course, I mean, I don't mean the objects. I mean the full strict subcategories generated by the objects. Okay. Okay, so yeah, okay. So before I move on, maybe one last fact, which is useful to have in mind, is that basically, so I said, what is a way of embedding these this dB of k of vector spaces into T, just by requiring the image, I mean the object E to be exceptional. But it turns out that this is enough to split off something. So this is the fact I want to mention, which says that subcategories generated by exceptional collections are admissible. Okay, so what does that mean? That means that there exist right and left adjoints. Okay. So for example, if you have the right adjoint, so you get a triangle of functors like this, which you complete into the cone, and basically this thing will project onto the orthogonal complement. So so basically, so given an exceptional collection, E1, En inside T, there exists A such that T is equal to E1 En A, and actually A can be I mean the objects in A are very explicit. They're all the objects that have no morphisms to the EIs. So they are T in T such that on T prime is 0 for all T prime and E1 En. Excuse me? Yes, I guess so. Yes, I guess so. Yeah. Okay, so this is for the general setup. So now I want to focus on very explicit triangulated categories. So the example I have in mind is just, as I mentioned, it's just the case of T equal to dB of coherent sheaves on X, where X is a smooth projective variety over K. Okay, so maybe the first and most famous example of exceptional collection is the Bailinson collection on Pn. So what is this? So this is dB of Pn, which is O01 On. So these are line bundles, but I see them as elements in the derived category by placing them in degree 0. Okay, so in this case, knowing that this decomposition is semi-orthogonal is just a matter of understanding the cohomology of line bundles on Pn. Then the tricky part is actually to show that, so maybe I should have defined over there that here, that so if A, so A equals 0, we say, so if we say that the collection is full. so it generates the category. So in that case, what's tricky is to show that, so the line bundles O, O, N generate your category. Okay, so I won't get into the details. So let me give another few examples. So now if you take, if you take P2 blown up at a point, so and E the exceptional divisor, then in that case, dB of P2 star is just O, so I can never remember, OE minus 1, O minus 2, O minus 1, okay, and more generally, there's a blow-up formula due to Orloff. And then there are plenty of examples. So for example, there is the smooth projective quadrics, so over C. So in that case, so this is due to Kep runoff, maybe 15 or 20 years ago. So dB of Qn is equal to S, so O, O1, O1 minus 1, or S, so S minus, S plus, O1 minus 1, and so this is if n is odd, and this is n is even, and those things, so I'm not going to get into details, but S minus and S plus are spinor bundles. Okay, and then there's also another example. There are other classes given by Kep-Runoff, which are given by Grassmannians. In the case of Grassmannians, it's more of a combinatorial matter to explicitly give the exceptional collections. So again, this is over C. And in fact, there's a sort of conjecture on rational homogeneous spaces. And the conjecture, so it's an ongoing conjecture. So we have K equals C, G a semi-simple group, and P inside G a parabolic subgroup. Then the conjecture says that there exists an exceptional, so a full exceptional collection for dB of G mod P. Okay, so this conjecture has been proved in many, many cases, and I mean, some of the remaining cases include G is E7 or E8. Sorry? No, it remains. The proof, yeah, it's still open. I'm not sure. Because I remember reading a proof for G2. Okay. I can't say. Okay, so so as you can see, all the examples of varieties here are pretty special. So in fact, the existence of exceptional collection is pretty restrictive on X. So what are the first restrictions we can find? Okay, so I have two types of restrictions. Okay, so let's first start by because the existence of non-trivial semi-orthogonal decomposition is usually quite restrictive on X. So here it's not by exceptional objects, but just semi-orthogonal decomposition. So for example, if X is a Calabi-Howe, so for example a K-free surface, then dB of X has no no non-trivial semi-orthogonal decomposition. Okay, why is this? Well, I mean, the proof. I think the proof is due to Bridgeland, and the proof is like this. You write dB of X as A, B. So this is to give you a bit of flavor of the techniques involved. Okay, so by definition, that means that there are no morphisms from B to A. But then by Serre duality, so here dimension n, A, B is B, so A tensor canonical divisor shifted star. Okay, but then canonical divisor is trivial, so this is just BA shifted. But then by definition of semi-orthogonal, this is 0. Okay, so if you have a semi-orthogonal decomposition, then it's actually a completely orthogonal decomposition. This implies that dB of X, so let's write it like this. It's just A plus B. Okay, so then the idea is to say that the structure sheaf OX belongs, because X is connected, belongs either to A or B. So let's say it belongs to A. Then we consider the sky scraper sheaves OX, and because OX is non-zero, this implies that OX belongs to A. Okay, but then the elements in B have no morphisms to skyscraper sheaves, so they're all 0. Okay, so I'm not writing all the details, but this implies that, so for all B in B, B OX is 0 for all points, which implies B equals 0. Okay. So this is a geometric restriction. Yeah. So I think maybe I should really write Bridge. I think it's due to Bridgeland. Okay. So now I'm coming to the type of restrictions I'm basically going to consider. So, okay. So I should have mentioned this before, but if you have a triangulated category T, which splits as A, B, then basically if you take the K0, what you get is K0 of T is K0 of A plus K0 of B. Okay. So now, so since so if E is exceptional, then so the subcategory generated by E is just isomorphic to equivalent to dB k vector spaces, and so K0 of E is just equal to K0 of k vector spaces, which is just Z. Okay. the point now is that the existence of a full exceptional collection well, implies that the K0 of the variety is actually free of a finite rank. Yes? Yeah. Yes. Yes. Yeah, there's a base change theorem due to Kuznetsov, and basically you just pull back in. Yeah. Okay, so yeah, so my point now is that if x, so when I say that x has a full, I mean dB of x, of course, has a full exceptional collection. So dB of x equal to E1 En. Well then, K0 of x is just Zn, and the basis is given by the classes of the EIs. And in fact, we even have, so again, by the base change theorem, you have an exceptional collection for dB of x pulled back to any field extension. So for example, if K is a subfield of C, then you even have K0 of xc is equal to Zn. Okay, so as was mentioned in the previous seminars in the past few weeks, what we get by the Riemann-Roch is that the child ring of xc is finitely generated, or finitely spanned, I guess, well, okay, let's not say group, but let's not say ring, but group. So we have the Chern character from K0 of xc tensor Q. So this says that Chow star of xc tensor Q is okay, let's say a finite dimensional Q vector space. Okay. So by the technique of Bloch-Srinivas, we get that the Chow motif of x with rational coefficients is isomorphic to a direct sum of Tate motifs. So Tate motifs are just motifs of points shifted, or twisted, maybe I should say. Okay, so for example, this implies that H star, so the cohomology of xc with Q coefficients is spanned by algebraically spanned, so spanned by algebraic cycles. Okay. Okay, but so what I want to mention now is that, so here there's a clear link between the existence of an exceptional collection and some motivic properties of x, but in fact the existence of exceptional collections is much stronger than a splitting of the motif. I mean, there's much more to construct. But so anyhow, so in some sense the derived category of x, dB of x, captures more or maybe different aspects of the geometry of x. And so for example, maybe I should say that, so if x is a surface, so a smooth projective surface, so it is conjectured that the existence of an exceptional collection implies that x is rational. Okay. So in fact, it's possible to prove the following proposition for surfaces. So for surfaces, I mean, this condition here, so dB of S is equal to E1 En, actually implies that the Chow motif with integral coefficients is a sum of Tate motifs. Okay, so this is with Z coefficients. And in fact, this is not at all expected to be an equivalence because for a surface, well, yes, because you blow up points on. Yeah. Okay, so for surfaces, you can actually prove this, and the reason is essentially because you don't really need to tensor with Q the Chern character. Yeah, so I was about to say that this is this is not an equivalence, or it's not hoped to be an equivalence because so for example, if you take S a Barlow surface, so by results of Awo, Colliot-Hélène, Paris-Mallat, yourself, the Chow zero is it's called universally trivial, so it stays equal to Z after any field extension, and makes it possible to prove that the Chow motif with Z coefficients is also a sum of Tate motifs. So. But then if you consider dB of S, so this has been considered by Bunning, Graf von Bottner, Kapranov or Kazarkov, I can't remember, Kazarkov, and Sosna. So they showed that this has, so there's an exceptional collection, E1, E, how many are there? 11? And A. And K0 of A is 0, but A is non-zero, so this is called a phantom. So this doesn't quite prove that the Barlow surface doesn't have a full exceptional collection. It proves that there's one where there's a phantom left. I mean, you can't say that. I mean, there's no. For example, in the case of projective space, in the case of a Bailinson collection, we know that all exceptional collections are basically spanned by this one, by the group action given by mutations. So, but in those cases, it's not clear whether this implies that there's no full exceptional collection. Yes, I thought about this, but I think you still need to construct all those morphisms between E1 and you've got morphisms from the left to the right, so it's not clear, I think. Sorry. Okay, yeah, so as you mentioned, I'd like to mention the bond. Yeah, you don't know the maps, that's the trouble. And in fact, it's actually quite difficult to show that this A is non-zero. Okay, yeah, so at that point, maybe I should, as you mentioned, so dB of X, as I mentioned, captures a lot of the geometry of X. So this is, as you mentioned, you can see it through the very famous theorem of Bondal and Orlov, which says that if you have X and X prime, two smooth projective varieties, kx's, so plus or minus kx is ample. Then, so dB of x equivalent to dB of x prime implies x isomorphic to x prime. Okay. And there's another theorem I'd like to mention. I mean, it's not as deep, but I think it's nice enough, which is due to Bondal and Polischuk. Which says the following. So if dB of x has an exceptional collection consisting of pure sheaves, then x is Fano. So, for example, in the case of the Barlow surface, with the way this is constructed is by using line bundles. Sorry? Yeah. Yeah, I think so. I don't think so. No, I think it implies or maybe, let me think. I have to double check. Maybe you have to either assume it's that plus or minus kx is ample. I'm not sure. Yeah, of course. Yeah, sorry. Yeah. Thank you. Okay, so before I move on to surfaces and the Neron-Severi lattice, as mentioned in my title, I'll mention one last proposition. So this gives a characterization of projective space. So it's the following. So we have x smooth projective over k, and okay, so at that point we need the characteristic of k to be equal to 0. So we assume that dB of x is L1, so L0, Ln. Okay, so the Li are exceptional. So this time line bundles. So this is important. Then x is isomorphic to Pn. Okay, so I would have liked to say something about the proof, but sorry? Yes, x smooth projective is, thank you. Yeah, if I scrap half the assumptions. Yeah, so if you think of the criterion on the K0, then you see that n plus 1 is the minimal number of exceptional objects for a variety of dimension n. And in fact, that says that at least tensor with Q, the cohomology is generated by one line bundle. So you get that x is here is isomorphic to Pn. So the assumption on line bundles is very important. I mean, if you remember the odd dimensional quadrics, then that's not true. It's no longer true. So the proof is actually so this is what I've been doing lately. I mean, basically the proof. So you use the Bondal-Polischuk criterion that tells you that x is Fano. Then you know that K0 of x is z n plus 1. Then K0 of x is torsion free, so you get that pick x is torsion free, and then the rank has to be 1, so pick x is just generated by one class. So all the line bundles Li are of the form OAIH for some integers AI. And then basically, so you know that Li and, for example, Li and Lj are orthogonal, so you know that, so the Euler characteristic, which is -1 power L Li Lj shifted by L will be equal to 0 for all I bigger than j. Okay, but then this is just P of A j minus AI, where P is just given by Riemann-Roch. So let me write it here. So P of A, which is chi of OAH, is just equal to degree of Hn over factorial n an plus degree Okay, but then because we have exceptional line bundles, we know that chi of Ox is 1, so the polynomial is non-zero. It has at most n roots. So you find restrictions on the AIs. In fact, you show that they belong to an arithmetic progression. And then you just plug in everything in the polynomial, and what you find is that the degree of C1x Hn minus 1 is plus or minus n plus 1, and that the degree of Hn is 1. But then you know that that pick x is generated by h. You know that x is Fano, so this condition here implies that C1 of x is n plus 1 times an ample divisor. And then there's a criterion of Kobayashi and Ochiai. Which implies that at least if you pull back to C, Xc is isomorphic to projective space. But then you have a zero cycle of degree 1, so this implies that so X is split, so X is just Pn. So the proof is deceptively simple. Sorry. No, the only reason is because this criterion uses characteristic 0, and there's no, it uses it in a crucial way. This is the only place where you need.
Yeah, sure, but do you expect it to be true, or?
I have no idea. Okay, so here I mentioned the numerical criterion. So now I want to move on. So now everything's going to be much simpler than all these derived categories. Yes, yeah, because of this example of the quadrics, odd-dimensional quadrics. Oh yeah, maybe I should mention. Sorry, I forgot to mention, but the reason why I looked at this was because of a recent preprint of Galkin. Sorry, I can never remember. Kapranov or Kadzarkov? Sorry? This one's Kadzarkov, okay. Sorry. Millet and Schinder, where they consider a class of varieties X called manifolds. So manifolds are, so X of dimension n. So these are varieties that admit an exceptional collection of minimal length, so of minimal possible length, which is, as I mentioned, n plus 1, but this time by objects EI, which are in the derived category. And they've started a classification, and so for example, in dimension 3, they find all such varieties, but it really relies on classification results. And I mean, basically, they show that in dimension 3 that they are all Fano because basically there are no projective spaces of dimension. And then they give a complete classification. So, for example, it includes quadrics of dimension 3. And my impression is that maybe manifolds are necessarily Fano, but there's no proof. Okay, so I mentioned this numerical criterion. So as you might have seen here, I've replaced the basically here, I didn't use the full fact that, at least for this equality, that the collection was semi-orthogonal, but I only used that the Euler characteristics were 0. So this is the definition I want to make. And the definition is that, so a numerically exceptional object E is an object such that mod chi of EE is 1, and then so a numerically exceptional collection is a collection E1, En of numerically exceptional objects such that chi of Ej, Ei is 0 for all j bigger than I. Okay, and then so if you have X smooth projective, a numerically exceptional collection E1 En is of maximal length if the rank of K0 of X mod the kernel of the kernel of the Euler pairing. So basically, this is a basically numerical equivalence under Riemann-Roch is equal to n. Okay, and so of course, the obvious remark to make is that, everything that's exceptional is numerically exceptional. Okay. So the reason for looking for these is, so recently there's been a lot of interest in exhibiting exceptional collections for surfaces of general type with PG equal Q equals 0. So many people have succeeded, and it's quite a lot of hard work. But the key point is first to exhibit quite a lot of numerically exceptional collections, and then to basically do a lot of hard work to show that one of them is actually exceptional. So basically, you have to lift some numerical conditions to, basically some alternate sum of groups to the groups themselves. So this was the reason I started looking at this. And in fact, for surfaces, there's actually there's a numerical criterion to determine if a surface has a numerically exceptional collection of maximal length. And so it's the following. So this is the theorem. So we start with S surface over, so a smooth projective surface over the field K, and we assume that chi of OS is equal to 1. So then the following are equivalent. So the first one is S has a numerically exceptional collection of maximal length. Okay, so let's call it okay, so I'm E0, En plus 1. So why am I using this is because that so maximal length here just means that n is equal to the rank of n1 of s, where n1 of s is just divisors modulo numerical equivalence. And 2, so we have ks square is equal to 10 minus the rank of n1 of s. And one of the following holds. So either, so n1 of s is unimodular of rank 1, and ks is 3 times a primitive divisor, or n1 of s is isomorphic to the hyperbolic plane, and ks is twice d for some primitive d, or n1 of s is odd unimodular of rank bigger than 1, and ks is primitive. Okay, so I can't lift that board. Okay, so it's fine. Okay, so I'll say a word about the proof in 2 minutes before I want to give. Sorry?
Why that assumption?
Oh, it's because, so I think the problem is that, so if one of the EIs is a pure object, I mean is a vector bundle, then you can drop the assumption because chi of EI will just be chi of EI tensor EI dual and equal 1, so you get what you want. But in general, if these are just complexes, then I mean I don't see how to deduce that chi of OS is 1. I mean, it's in some sense, it's a minor assumption. It's kind of the key assumption to get exceptional collections anyway. So there are, okay, so I'm going to be a bit quick, but there are 2 sort of consequences. Excuse me? In N1, yes. Yes, in N1, yes. So yeah, I should have been more precise. Thank you. So there are 2 types of consequences. So the first one is sort of arithmetic. So this is a bit strange to me, but so this formula should remind you of Nefer's formula. So basically, if you're over an algebraically closed field, let's say you're over C and you assume PG equal Q equals 0, then of course this will be true. This is just Nefer's formula. But actually you get it without any assumption. So my point is that we have the following corollary. So if you have S with, so chi of OS is 1. Actually, I'm also going to assume that, so in case we are in positive characteristic, I'm also going to assume that H1 of SK bar QL is 0. So S with a numerically exceptional collection of max length. And then So the cycle class map to tensor ZL. So if you mod out torsion, this is surjective. Or you could also find that N1 of X under base changes, this is always an isometry. So what this corollary says is that basically on the surface, an exceptional collection, a numerically exceptional collection, which is of maximal length, remains of maximal length after any field extension. No. That's the intriguing thing. You don't assume a K algebraically closed, but you still get this formula. And I'm gonna show how you get it. Any extension, yeah. Yeah, because the Neron-Severi group doesn't change after extensions of algebraically closed fields. Okay. What else do I want to say? Yeah, okay. Yeah, so, okay, I'm not going to write it, but for example, there's maybe 5 years ago, Hilo and Perling gave a very nice construction of, so they started with a surface with, I mean, their assumptions are stronger, but you can weaken them a bit. They started with S a surface over C, which has a numerically exceptional collection of maximal length, and they were able to attach to this surface what they called a toric system. And from that toric system, they can construct a toric variety. So to any sort of numerically exceptional collection of maximal length, they can attach canonically a toric variety. And basically this, and in their proof, they use in a crucial way the Neuffer's formula. So they assume that PG equal Q equals 0. And basically this theorem extends their result to any field. But there are also well, the thing is, sorry? No, because it's CH1 mod num, so the torsion is killed. Yeah. Yeah, mate. Thanks. Yeah, I should have insisted on this. I mean, both the rank. I mean, the rank is already maximal by this formula. But yeah. It's but it's unimodular. Yeah, that's because yeah. Thank you for. Yeah. So yeah, it's. Okay, I'll say a word about the proof. Okay, the proof is very. It's just linear algebra, so everything comes from linear algebra. It's very strange.
What examples of this? I mean, kind of you said a minute ago that the essentially.
But basically, this theorem says that a surface over a non-algebraically closed field, if it's not split, then basically it will never have a numerically exceptional collection of maximal length. That's basically what this says. Yeah. No, but for example, if you take the Barlow surface over C, it will have a. Yeah. Okay. So maybe okay. Let me give the geometric consequence. So now I take S, let's say a complex surface with PG equal Q equals 0. Okay, and if the Kodaira dimension of S is 1, we assume additionally that that S is not minimal. Then S has a numerically exceptional collection of maximal length if and only if S is not Enriquez. So basically we find that every surface which is not Enriquez has a numerical exceptional collection of maximal length. So at least, I mean, for general type, it will work. And then there's the case of Kodaira dimension 1. So in that case, there's a classification of surfaces. These are Dolgoshev surfaces. And in this case, actually, you can do a case-by-case computation to check whether or not these assumptions are satisfied. So I don't have time to do it now, but you can really run it. So actually, you can, given a complex surface with PG equal Q equals 0, you can decide whether or not it will admit a numerically exceptional collection. So this gives an obstruction to the existence of exceptional collections. So for example, for an Enriquez, this shows that there's no exceptional collection of maximal length. So for example, people had tried to construct exceptional collections, and so what you expect is an exceptional collection of length 12, and I think Zube has constructed one of length 10, but actually this shows it's not possible to go, I mean, at least to go to 12. So I'm sorry, I'm just going to run over for 2 minutes. I just want to mention the proof because maybe some people in the audience can give me some insight on the proof. Okay, so the proof. Okay, so in some, the most difficult part is 1 implies 2. So the first step is just to reduce to EI of rank 1. So this has recent, I mean, this uses a strategy used by Perling recently. The idea is you start with E1, E0, En plus 1, and you do mutations, and you play around, and you can find one which has where the elements have rank 1. So the rank is, so I mean, if you have a complex, you just take the alternate sums of the ranks. Yeah. Okay. So then you can reduce the problem to linear algebra by taking first rank class and doing Riemann-Roch. So the point is to define a divisor di to be C1 of EI minus C1 of EI minus 1 for 1 less than I less than n. So, okay, so I'm ignoring the last term. So these are elements in SHA-1. Okay, so by Riemann-Roch, what you find is the intersection matrix. So it looks like this. Okay, so it's tri-diagonal. And of course, AI is just di square. And you also find that ks.di is just minus di square minus 2. So you find that ks is minus m minus 1 of a1 plus 2, an plus 2. Okay. So then the first step is to show that, so the first is to show that M is unimodular. Okay, so I'm going to skip this because this is well understood. And the fourth step, so the fourth step is actually a result of, it's just linear algebra. You start with M equals A1, 1, AN in GL and Z. Okay, and you assume that the signature of M is 1 n minus 1. So this is the case in our geometric situation by Nefer-Lefschetz. Then these only two conditions imply that there exists an index I such that AI is minus 1 or 0. So combined with the unimodularity of M, this gives the primitive thing for KS. The proof is horrible. It's just a row column operation and I mean, using divisibility. I mean, it's very strange. And the fifth step is very puzzling to me. You are in a very general situation. So if you want to compute KS square, you just need to compute this. Okay, so basically given a unimodular lattice, a a unimodular matrix like this. I want to compute that number, so this is a polynomial in the AIs. And so I haven't proved, so it seems that this number only depends on the signature of M. So of course, I have a proof when the signature is 1 n minus 1, and I can show that this number is always 10 minus n. So the proof in that case uses, again, this. Basically, I do some row column operations to produce a minus 1. There are only zeros. Then I do a blow down, and I can do induction. But it's really nasty because you have to check that like values of this form stay of this form. And so hopefully I'll find a more conceptual proof at some point. But at least this result is very strange to me because you have polynomials, which you have basically two sets of polynomials which agree only at integers. They don't agree if you add, for example, I to your ring. Okay, thank you. I'm very sorry for running.